Okay, so as we finalize our revision and work towards our exams, so we're going to go through some basic questions coming from test papers and exam papers. And these are the questions that you guys shared that we'll look at tonight. So we'll start with questions from here, and these are actually very basic. So the question then is, how do we work them out if you find them in the exam? How do you approach them? So, what do you do? Let's, okay, so let's do this. Okay, so let's start with this one. Okay, so for the first question, I will skip the units unless if someone wants to see how to handle those. But I will skip these, assuming that you're comfortable with them, and then we move on to look at part. So if you have an issue with those, you can just speak out so that we look at them as well. If not, then we'll start with question 1B. So what is happening in question 1B? So question 1B, we are looking at systems of a system of three concurrent forces is shown, for example, in 1.1. Determine the magnitude and direction of the resultant. So for this one, this is basic first year physics where you're given vectors. And if you recall from there, the easiest way to approach these is using components, as in just creating a simple table. So let's see who's joining us. Let's allow. Okay, so we'll proceed. Okay, so the best way to deal with vectors from a first year point of view is to use a table. If you want, you can still use the approach we did in second year, where if you're going to get the resultant of multiple forces, you can express them in vector form. But you can still go ahead and okay. So here they're saying that we have a system of three forces, F1, F2, and F3. So we're going to create a row for each one of those forces. So if you recall, this is basically what we were doing in first year. And then the last row is going to be for the resultant. So we have F1, F2, and then we have F3. And then the resultant is going to go there. Or let's go R. So split this into two parts for each component. This is in 2 dimensions. That's why this is actually even easier to deploy. In 3 dimensions, for simplicity, we'll always just go ahead and look at vector form expressing vectors. So, and then we'll get the result, and we'll see that. I'm sure it will come up. So you have X components here, the Y components here. Observe that I'm sticking to the basics right from first year. The force F1 is given as a 50 Newton force. Now, instead of giving us an angle, look at what they've done. They've given us that small triangle. So we can use the ideas of similar triangles to say if the angle here is, let's say, theta, even the angle here would also be theta, since each one measures from the horizontal to that straight line. Based on that, since this is a 4, when this is a 3, and this is a 5, then we can use that small triangle to predict what cos theta is, cos adjacent over hypotenuse, which is 3 over 5. And then you can also predict what sin theta is, sine opposite over hypotenuse, which makes it 4 over 5. Now, when we try to get the components for the bigger triangle, if we go for the bigger triangle now, what we have the Y component there, we have the X component here. Observe that the X component will be given by cosine. So the X component will be equals to the vector itself, 50, and then cosine the angle theta. But I already saw that cosine is 3 over 5. So you have 50, and then we have 3 over 5 here. In the same way, okay, we can divide 5 here or 10 times there, so that you have 10 by 3, which is 30. So basically, that is what we're going to have there. So again, 5 in 5 will cancel with that, giving us 10, 10 by 3, that is 30. I hope you guys are following what I'm doing. Just make sure that we get the correct answers. We can also get y. Y will be this side given by sine, since they are opposites, so we'll have 50. And then we have sine theta. So sine from that small triangle, so that sine was 4 over 5. So this is 50 times 4 over 5. 5 will go 10 times into 50. 10 with 4 will give us 40, giving us this as a 40. So you've seen that for F1, the components are coming out as 30 for x, 40 for y. So you have 30 for x, 40 for y. I can put the units here just in case I'm being marked by someone who is strict, so that I don't even have to repeat units in these columns. So I have obtained the components for F1. Now I need to do the same thing for F2 and F3. So notice that in each case, they've given me different descriptions to help me get the components. For F1, they used a small triangle. For F3, they've just made it to lie along one axis. For F2, they've actually given me an actual angle. So they're literally trying to see if you can get components here for different scenarios. Look at F2. F2 is given to be going this way. And then look at the description. So pay attention to every detail here. Look at the way they're describing F2. It's easy for you to miss it. If you've seen it, if you've seen questions like this before, it should be easy for you to follow. So they're describing by saying, hey, the thickness or the angle from this line to this line here, the angle between them is 15 degrees. So in other words, they're saying the angle here is 15 degrees. So the angle between F2 and the vertical is 15 degrees. So this way we can easily get the components by creating a right angled triangle here. So if we claim that this is right angled, the vertical will be y, the horizontal will be x. So if we wanted to get the x component, it is opposite to that 15, so it will be given by sine. But it will be going to the left if you follow that arrowhead. So it will be minus, then it will be the vector itself, which is F2, so that is 80, and then sine 15. Then to get the y component will be side by side with the 15, so adjacent, that is cosine, and it will also be going downwards, so minus 80 cos 15. So this was for F2, and then the components just like that. Alternatively, you could have chosen to measure your angles from the positive x-axis anti-clockwise. So you could have chosen to measure it from here all the way up to, and not there, from here all the way up to here. Notice that to get this angle, you'd have had to subtract from 270, you'd have had to subtract 15. That would have given you exactly what this angle is quite. But after obtaining it, you now would have just used the fact that x can be obtained by cosine. So you'd have used 80 cos whatever this angle phi is. And then what would have been obtained by sine? 80 sine phi. And you know this method, if you use this angle measured anti-clockwise from the positive x, it will even tell you that x coordinate and y component also negative, even though we do not do that analysis here. So this is an alternative approach that some of you might have preferred. Next up, F3. F3 is more straightforward since it lies on an axis. What does it mean? F3 itself is an x component. And this force F3 has no component in the vertical, so the y component is 0. The whole of F3 lies in the x-axis. The only thing you had to check is it in the positive x or in the negative x? It's in the positive x. It's going to the right. So it has to be positive. And you're done. So all you have to do now is add the x components to get the resultant in the x, and the y components to get the resultant in the y. Can you try to add that? What are you getting? Okay, so you've seen that these are the components that you get. Once you obtain the components, what is the question I'm asking for? They want us to determine the magnitude and direction of the resultant force. So they want the resultant force. To get the magnitude of the resultant force, we can use Pythagoras theorem. So this would be root of the x. Yes, please. Okay. It's what? The x component, 9.294. And the y component, it's okay? Okay. So to get the magnitude now, you can use Pythagoras theorem. Whatever your x, yes,
The value that she got is those were like the same value that we also got 39.2944769.
294. Okay, so these were correct.
Yes.
Okay. All right, so just be very careful, guys, with the calculators. I think maybe you might be having issues here. Just put that in bracket, and let's see how I would approach it. Hope this will have the sign. Yes, it does. So if I want to do everything there, I'll do 30. Then I'll have plus. Then I'll put the bracket. Then I have minus. Now that's 80. And then that's sine 50. Then I'll close my brackets. Make sure they are all closed there. And then I have plus 30. So plus, no need for brackets there, plus 30. So that's 39.294. So yes, that value is correct. So assume the other value is also correct. So we can proceed. Once you have this, you can now just square the x component. So square the 30.294. And then plus. So when you have this negative here, make sure you use the brackets here. You have minus 37.274. And square should be outside of the brackets, that it also affects this negative. So once you obtain your answer, square root. What are you getting as the magnitude? 54.16. Okay. So when you check your values for the forces, they all had Newton. So even your answer for the magnitude will come with the Newton. This is the magnitude. To get the direction, you can start by trying to picture it. I always like creating this picture. The picture is obtained by using the components of the resultant. So this is y, this is x. So I don't want to use the numbers. All I want is the sign. The x component was positive, meaning the x component of the resultant was going to the right. So that is the x component. The y component of the resultant was negative, meaning it was pointing downwards. So these are the components of the resultant. From this, we can conclude that the resultant must have been a vector, or must be a vector that runs this way. This is where the resultant is actually pointing. This being the x component of the resultant, and this being the y component of the result. Even if I don't show this, what's important is me knowing the direction. So when I use tan inverse here to say theta is equals to tan inverse of the y component or the x component, you need to see that the theta you actually find is this angle here. Because when you now say tan theta, the opposite is the y component. The adjacent is the x component. So this theta is tan inverse of the y component. You have minus 7.274 over, and then you have 39.294. Write the top one properly. Minus 37.274. So when you do this, what are you getting?
$43.49.
43.49. Is it negative? Negative.
When you include the negative.
Include this negative. What the negative implies, it just confirms that you are in the fourth quadrant. Remember, tan is negative in the fourth and also in the second. Again, one thing that the negative can be interpreted means that this angle is measured clockwise and not anti-clockwise. So that can be your interpretation. But if you had obtained it as a positive value, as long as you viewed it this way, you'd have still known what to do next. Because now to present your direction, you are not going to just state it as 43.49 degrees. Either say it's 43.49 degrees clockwise. Clockwise from the positive x-axis. Now you've completely described that it is in the fourth quadrant, the angle 43.49 clockwise from the positive x-axis. But if you don't want to speak some English as you present your answer, you can just say direction. Now measure your angle the actual, the standard way. Angles must be presented anti-clockwise from the positive x-axis. So now to get that direction, you'd have to say 360 degrees minus that 43.49 degrees. Okay.
One, 216.7.
116.316. So this becomes the direction. And this concludes the first question. You have to expect it to be negative. The reason is very simple. Tan is odd because it's sine over cos. So if any of these is negative, you expect it to be negative as well. But it doesn't really matter. Like I mentioned, as long as you can picture it here, as long as you can picture it there, you should be able to get the correct answer. Is that okay?
Yeah.
And yeah, okay. Why I was saying tan is old. Remember tan is sine over cos, and sine is old. So that is going to affect your answer. So making tan also to be old. Okay, so that concludes the answer for part B. Now leading us to part C. In part C, we now have this problem here. Yeah, we now have that problem there. For this problem, what are we looking at? We have two forces, F1 and F2, as shown. Determine the following: magnitude of the resultant of the two forces, the coordinate direction angles of the resultant force, the angle between F1 and F2. This is a very good problem because now it steps out from first year and now requires us to use concepts from second year. Let's get this and let's analyze it on its own. Okay, so what do they want us to do? First, two current forces F1 and F2 are shown. Determine the following: magnitude of the resultant force F1 and F2. When I analyze this, I see this X, Y, and Z. So I now quickly abandon the use of a table. It can work that table thing, but for uniformity, we know to say when dealing in 3 dimensions, we decide to represent each force in Cartesian vector form. Above all, we're going towards coordinate directional angles there. So see where they'll come up. Another reason why I'm going towards Cartesian vector form is the third question there, the angle between F1 and F2. Should recall, which method do we use to get the angle between two vectors? What do we use? So it should ring in your mind the dot product. Cross product as well, but dot product is easier. So elimination between two vectors, so not use these as forces. We take advantage of them vectors. So you need them in the form. So I need to get, or we get these forces in vector form. So we have how many? There are two of them. One is this one here, the other is this one here. Let's start with F1. So we need F1 in vector form. So in vector form, F1, we need the x component of F1, I, plus the y component of F2, F1, J, plus the z component of F1, K. When we look at it, we need to pay attention to every single detail they've given us. Look at this line here and this line here. What do they represent? Notice that these two lines are parallel to the axis. This line, for example, is parallel to the z-axis, which is here. This line is parallel to the y-axis, which runs through this part. What are they trying to tell us? They're trying to spell out to us that the force F1 lies on the YZ plane. So it lies strictly in the YZ axis. And if that is the case, then it doesn't have an X component. So it only has a Z component, downward component, and a Y component. So already, but X is 0. All I need is to find Y. To find Y and Z, we see that again, they've given us a small triangle to take advantage of. They're saying that if Y is 4, not Y, that's Z. Z is 4, Y is 3, and hypotenuse will be 5. That's what they're giving us. So we can use these to understand the components of F1. So in the same way, we can say that we can use an angle at the bottom here, we can use an angle at the top here, completely up to us. Let's use the angle here to the vertical. So if we use the angle to the vertical, which will be the same as this angle here, same as that angle there, Then when I use cosine of that angle theta for the small triangle, which is like this, an angle theta, which is here with this as 4, this as 3, and this as 5, cos theta with 4, sine theta will be 3 or 5. Once I have those, I can now use the understanding of sine theta and cos theta to describe what is happening to the bigger triangle. The force vector is going this way, and its magnitude is 450 newtons. So the y component is coming, not y, sorry, you saw use vertical being y, but in this case, understand that one that seems more horizontal is y, the one that is vertical is z. So the z component is here, the y component is here. So if I wanted to get, let's say y is opposite to this angle, theta, so it's sine. So when you have y is equals to the vector itself for 50 and then sine theta. But we already know that sine theta is 3 over 5. So it becomes 450. And then we have 3 over 5. What is this product? Is it 270?
Yes, that is correct.
Okay, so these are in newtons, the forces, so we go with newtons there. In the same way, we can get the z component. Now, in this case, the z component, we saw that it is pointing downwards, so we'll take it as negative. But it is side by side with the angle theta, so we use cosine. So it will be negative. The vector itself is 450, then cosine theta. Again, cosine theta from the small triangle is understood to be 4 over 5. So you can say z is equals to minus 450. And then that was 4 over 5, so you have 4 over 5 like this. So if you do the math, we should get minus 360. Is it?
Yes, it is.
So now that we know y and z, x was already understood to be 0. So f1, cos vector f1, x component 0, y component 270, z component minus 360. So the units, we have the Newton. This is F1. We now want to do the same thing for F2. For F2, however, we're not given a small triangle like for F1. Instead, we give angles. And in this case, observe that they have actually given us the directional angles for F2. That's for F2, yes. They have given us the directional angles. So the directional angles alpha, beta, gamma. Alpha is the directional angle between the x-axis and the vector. Beta is the directional angle between the y-axis and the vector. Gamma between the z-axis and the vector. We should recall that cos alpha relates the y component of the vector, the x component of the vector, to its magnitude. In the same way, cos beta relates the y component to the magnitude of the vector itself. And finally, cos gamma will relate the z component to the vector itself. So what does this mean? In this case, notice that the vector of F2 is 525 newtons. This is the magnitude. Now, let's start with x, the directional angle from the x-axis to the vector. From the x-axis to the vector, they've given us that 45. So for this, you really have to pay attention to the details. The 45 might have been easy to see. That is from the x to the vector. So how about the others? So alpha from the x to the vector is as big as 45. So from here, we see that cos 45 is equal to the x component, which is the x component of the force over the magnitude, or the x component to be equals to the magnitude, which is 525 cos 45. So we can say F2 is equals to 525 cos 45 I. How about the y component? So for the y component, magnitude of the vectors is the same thing that 525, but now we need the directional angle for the y-axis to the vector. Just find the y-axis. This is the vector, an angle being measured from it is this line here. So observe that this line here runs from here, it comes here, breaks, then continues until it reaches here. You're telling you that from here all the way up here, the angle is that 120. So that is not better, 120 degrees. So from here, you can easily get the y component as you saw for alpha, how it reduced, or you can use this to make the y component subject here. The y component will be equal to the vector itself, 5, the cosine, the directional angle 120. So bring here plus 525, and then we have cos 120. When you see this approach, don't worry about is it to the left, is it to the right? These angles are measured from the positive of each respective axis. Based on that, they will sort out the direction of the arrow. And it has to be that they're measured from the respective positive axis for that to apply. We go to the final component, the z component. The magnitude is still at 5 to 5, but we now need the directional angle from the z-axis. So from the z-axis, what do we have? See that again, it might have been hard for you to see, but this 60 is actually doing the job. See where the 60 is. It starts from here, breaks to accommodate the 60, then ends here. We do have to pay attention to that to see that. Otherwise, you might think it's coming all the way up to there. But that is where the 60 is. From the z, positive z again, to the vector. So that is our gamma. So based on that, the z component will be the magnitude, then cos the directional angle. So that's 525 cos 60. What is okay there? And we're done. Once you're there, since there were only two forces, it means that we'll only do this. To get the resultant now, just add the part with a J on F1, there is not J, I. There's no term with an I on F1, but on F2, we do have the term with an I. When you evaluate 5 to 5 cos 45, what are you getting? So now the part with J on F1 is 270. On F2, there is 5 to 5 cos 6 cos 120. So what will this be? So if adding, when you get the result, you're adding. So you have cos 120 multiplying 5 to 5 plus the 270. What are you getting?
0.5.
Like this. Okay, so that has been verify this. So now you go to K. Okay, you have minus 360 plus this. What are you going to get there?
It's 97.5.
7. So see how I am not living out the unit. It's a false, so it must have the unit. So we have obtained, yes, please. Is it, it's negative?
It's supposed to be
Degree. It's negative? Okay, so that's done. So once you've done that, you add your force. Remember the goal. The goal is to get the magnitude of the resultant of the two force vectors. So we're going for the we're keeping going for this. It's magnitude. So to get the magnitude now, the resultant, you can use Pythagoras theorem. Okay. So it's going to be 371 into 3 squared plus 7.5 squared plus minus 97.5 squared. So what are you getting there? What's that? What we do? Okay, so the others can verify this. Okay, so once you've obtained that, that answers the first part one, the magnitude of the resultant. The next part, the coordinate direction angles of the resultant. So to get the direction angles, that is for the resultant. We saw the coordinate angles for F2. Now for the resultant. We know that cos alpha is equal to the x component over the magnitude. This is for the resultant, not one of F1 or F2. So this is for the resultant. So here when I use Fx, I mean Fx for resultant. So it will be, I'll just use R for the resultant. So I can say the magnitude, I'll take it as R. So it will be the x component of R divided by the magnitude itself. So that the direction of alpha will be equals to cos inverse of the x component of R over the magnitude of the result itself. So this will be cos inverse. The x component, when we go back, the x component is the one that had I, which is this. Divided by the magnitude of R. So the magnitude of R here is what we obtained here is 383. So we divide and then we get cos inverse. So what will be our answer? Okay, the others can verify that value. So as you go on, yeah,
Wait, 308.
yeah, how getting a value is different. Can someone else give us their value? We see which one is good. In the same way, we can get cos beta, but it's going to be the y component or the magnitude. So that beta will be equals to, let's go directly to here. Beta will be equal to cos inverse of the y component over the magnitude. The magnitude is this, but the y component is 7.5. So that 88.88. So that's it. So, and finally, by the same logic, gamma will be equal to cosine the z component minus 97.5 over the magnitude. What are you getting? Okay. So we have obtained the direction of both alpha, beta, and gamma for the result. In part 3, they're now saying the angle between F1 and F2. So it's a good thing we already have these in Cartesian vector. 1.5. Let's get this. Let me put you. Getting negative. You guys can verify that. This and this. What's happening? Let's see. 270 plus, that's 525, then cos 120. 7.5. You guys need to mind your calculators. Otherwise they will affect you. So please be conscious. What's the what? 270, we are adding, we are combining F1 plus F2. Give us the resultant. Do you see that? Then wrap on left. Let's see. So verified, we can proceed. Now we have obtained the direction angles and we're going for part 3. And in part 3, we're looking for the angle between F1 and F2. So to get the angle between two vectors, we'll utilize the concept of a dot product. We should recall that if you have two vectors A and B, their dot product will be equal to the magnitude, the product of the magnitude, multiplying the cos of the angle between them. So from here, if we wanted to get the angle between the two vectors A and B, we would have to divide the dot product by the product of their magnitudes. So the overall angle will now be cos inverse of the dot product over the product of the magnitude. So we see that to get the angle between two vectors, we first need the dot product of the two forces, the two vectors. For A and B, we utilize the force vectors to get the dot product or the angle between them eventually. So how do we get a dot product? So the dot product for F1 dot F2, we know it doesn't matter the order was in the value. Multiply the x components. So from F1 is not I, meaning the I part must have been 0. From F2, there is I, which is going to be 5 to 5 cos 45. Of course, we know that doesn't mean that this will be 0. Plus, now you go to y. From F1, the y part is 270. Remember, you're multiplying here times. From F2, the y part is this. So you have 5 to 5 cos 120. We know this is a 0, so you might as well leave it out so that we create room for this. So just say 0 here. Next, the z part. From the z part, this is negative 360. Multiplying 5 to 5 for 60. So when we evaluate this, what are we going to get? So let me also evaluate it so that we don't have a debate again. So please make sure your calculator agrees with what we're going to get here. Press whatever button you have to press till it works. So you have 270 multiplying, that's 5 to 5 cos 120. Then plus, now you have minus 360 times, or let me use this negative, minus 360 by 5 to 5 cos 60. Okay, now I'm sorted and getting minus 165,375. So this is what we're getting as the dot product. Is this what you're getting?
Yeah.
So now we can use our angle for our formula for the angle. It's causing this the dot product, we have minus 165,375 divided by the product of their magnitude. We don't have to start getting magnitude, but we already had a magnitude. So F1 magnitude was 450, F2 523. So we have 450 multiplying 5 to 5. So multiply those, get the inverse, divide there and get the inverse. What would be the answer?
427.
427,
No, 134.
134.
Yeah, 427.
Okay, so the others can verify this.
Getting the same.
Okay, great. So this becomes the angle between the two force vectors F1 and F2. And that's how you work out that problem. Any questions? Okay, so looks like there are no questions there. So you can proceed to look at the next problem. So there are two more sets that you guys shared. We have this, and we have the other one. Okay, so we have this one next.